Hello. I came across an interesting problem I wanted to share with you guys, and I found it in this book, which is really good. It's by Terry Chu, I think he's like head of the Southeast Asian Maths Olympiad, and he publishes these books. He's got a ton of them, and there's some very interesting problems in here. And I came across this one. This kind of caught my eye because there was, I don't know, just seeing one of those problems that looks very complicated, but once you kind of have a think about it, maybe there's a trick to breaking into it. So what I'd like you to do is pause the video, see if you can either solve it, which would be amazing, or maybe you can notice a few patterns about what's going on with the numbers here. I quite like this problem because I think it leverages a few strategies and ties them all together in a nice way. So pause the video, have a think, and then I'll explain to you how to solve this problem. Okay, first step is to probably consider the numerator on this fraction, right? The top part. You've got this series of sums, and hopefully you notice that it all sort of pivots around the 7. And I like this because that means that in a lot of ways, 7 is sort of the theme of this problem. This problem's about 7s. And it's fitting that 7 would be the center point that sort of pivots around here. When you're solving a sum like this, a series like this, you can use lots of methods, but one of the most popular methods is often called the Gauss method. So like I said before, this problem is going to incorporate a few different strategies. And Gauss method says the following: if I've got a series of numbers, I can actually combine the first and the last term to find these repetitive pairs that I can then use multiplication to sum instead of having to sum them in order. So instead of going 2 plus 1 plus 2 plus 3 plus 4 plus 5 and adding on that way, I could notice that 1 can connect to 6 to make a 7, 2 can connect to 5 to make a 7, and 3 and 4. So I've got 3 groups of 7. This is a mirror, so to speak. It's the same on one side as it is on the other in respect to the 7. So if there's 3 groups of 7 here, then there must be 3 groups of 7 here, and there are. Remembering that you can do addition in any order. So that might be a piece you're missing if you're not understanding what I'm doing at this point. So you've got 3 groups of 7, 3 groups of 7, and then a 7 here. So how many 7s do you have? 7. So I can rewrite this entire top part as 7 groups of 7. Now, one way to do that is, of course, to just write 7 plus 7 plus 7 7 times, or I can use multiplication. So let's use multiplication because that's going to help us solve the bottom part. So we're going to rewrite this as 7 times 7, which is really all that sum was, of 7 groups of 7. Okay, now let's look at the bottom part, the denominator. I've got 7 7s times 7 7s. I really don't want to do that, multiply those, so I'm going to think a little bit deeper about what's going on inside this fraction. And before I solve that, let's just take a look at a simpler case. So in problem solving, it's often really good to either try to generalize these problems or solve a simpler case and try to apply that knowledge to something like this. So suppose my problem wasn't this one. Suppose it was like this. 7 times 7 over 7 times 7. Okay, one of the things we might remember about fractions is that they're just ratios. So if we have a number on the top and a number on the bottom, then it's like we can divide that number into itself. So for example, a 7 can go into a 7 once, and a 7 can go into a 7 once. This actually just reduces to 1 over 1, or 1 whole. A little bit more going on behind the scenes there. Probably won't get into at the moment, but applying this knowledge down here, can you see what the next step might be? If I divide this top part by 7 and this bottom part by 7, then this turns into, right, 1 times 1, 7 divided by 7 is 1, over 7 ones, 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7 times 1, 1, 1, 1, 1, 1, 1. 7 ones. Oh, can we see that? Let's see. There we go. Okay, I'm going to rewrite this up here on the screen so you guys can see it, and then we'll continue solving. Hang on. One more step to go. This is one of the other reasons I love this problem. We've got the Gauss method, okay? We've got some identities about fractions that we're dealing with. And then we also have to draw on just a little bit of general knowledge about mathematics and some patterns that appear. And in competition mathematics especially, you can't get away from this. It's not just about the fundamentals, it's also about learning some tricks. And one of the tricks that we learn is what happens when you multiply numbers with the ones digit together. Let me show you an example of multiplying numbers with the ones digit together. So 1 times 1 is 1. Easy. Right, let's do 11 times 11. These are all going to be squares, by the way, so this is also a square number, right, because you're multiplying it by itself. You've got 7 ones and 7 ones, right? So 11 times 11 is 121. And if you research this, they often call it the 11's trick. Yes, it can apply to any number times 11. It doesn't just have to be 11, the square of itself. But anyways, I digress. Okay, next one. Can you see a pattern? It's as though you've got this sort of expansion from the center, this like mirrored expansion. Okay, I've got 3 digits here and 3 digits here, so I've got a 3 in the middle, and then it counts down from 3 to 1 on the ends. This is also a pattern that can produce Pascal's triangle, and yeah, but we won't get into that now. Okay, so let's keep going. So 4, 1, 2, 3, 4, 3, 2, 1. Okay, so if I follow this pattern, 5, 6, what should I get if I do with the 7s? Well, I might write it over here. Okay, 1 times 1 over 1, 2, 3, 4, 5, 6, 7 times 1, 2, 3, 4, 5, 6, 7. 1 times 1 is just 1. And then underneath that, I'm going to have the logical extension of this pattern, which is 1, 2, 3, 4, 5, 6, 7, 6, 5, 4, 3, 2, 1. There's my answer. So I really like this problem for a few reasons. I like that it's got this theme of 7. And at the very beginning, you might have remembered, it was actually just this sequence, but with pluses inside of it, right? And then we were able to turn that back into a number in that exact same sequence, obviously without the pluses. If I wanted to read this number, because it's hard to look at these sequences and think about them as numbers. They just sort of look like, to me, they just look like little patterns. This number is actually, what place value is it in? Well, I'm going to put every 3 digits here. So this is the millions, trillions. So there's a number in the trillions that you just multiplied. It's pretty cool. So there's your answer, and I hope you enjoyed this fun little problem. I'll see you later. Bye.